Good morning to everyone. In this video, we are going to learn about types of semiconductor. Types of semiconductor. What are the types of semiconductor? First one is intrinsic semiconductor. And then second one is extrinsic semiconductor. Let me see one by one what is intrinsic and what is extrinsic. The intrinsic semiconductor, it is a pure form of semiconductor. It doesn't have any external agency of another types of atoms. So it consists only the pure form of semiconductor. And then extrinsic semiconductor, it's a combination of somewhat impurities. So original semiconductor, it may be in the form of silicon or germanium. I'm going to add some impurities for the purpose of to increase the conductivity and the carrier concentrations. Okay, let me see one by one. Let me consider a solid bonding structure. Here I have shown the diagram of semiconductor bonding structure. The common used in semiconductor is germanium and silicon. Now I am here, the silicon atoms are binded to close to one. So each semiconductors, that is each silicon atom, will binded to the another silicon atom in the form of covalent bond structure. So covalent bond means 1 to 1. So here the silicon atoms are binded to the another neighboring silicon atom through the covalent bond structure. So one atom is given to the another neighboring silicon atom. This neighbor atom is given to the one electron to this neighboring atom. So the silicon atoms or electrons are sharing. Silicon atoms are having the 4 electrons. So 4 electrons are binded to 1. This is the like in the form of matrix formation. So in this structure, here 1 to 1 electrons are binded. This type of bonding electrons are called conduction band. Conduction band or conduction electrons. So the 4 electrons are here. This electrons come going to bind the another neighboring silicon atom. Here also. And these are the atoms, these are the electrons are called Valency Electrons. Valency Electrons. Because they are in the outermost orbit. These are all Valency Electrons. These are all Valency Electrons. So there is no electrons to carry the charges from one point to another. So in this intrinsic semiconductor, there is an insufficient of move the electrons from valency band to conduction band. If suppose I am going to give certain temperature to this intrinsic semiconductor, I already told you the intrinsic semiconductor is a pure form of semiconductor. So only having the all silicon atoms only. There is no impure atoms. So the conductivity is too low. For the purpose of increasing the conductivity, I am going to give the temperature. If you are supposed to raise the temperature value, one of the few electrons only break the covalent bond structure and it moves from valency to conduction band. If suppose the electrons will move from valency to conduction band, the bond will be broken. So it is replaced by the another empty charge that should be called as holes. It is equivalent to the electron charge. Electrons are having the negative charge particles. It is equal to electrons. So I am going to give the charge value of positive. So holes are positive charges. Very important one. In an intrinsic semiconductor, there is a number of electron equal to number of holes. Very important one. In intrinsic semiconductor, in the structure, if you are supposed to raise the temperature, the bonding will be break. So the electrons will move from valency to conduction band. It instantly the holes will be regenerated at the same place, that is empty place. So the number of electrons in the conduction band is equivalent to number of holes in the valency band. So how many number of electrons move from valency to conduction, that much of holes will be regenerated in the same place. If suppose the temperature can be considered as 0 Kelvin, the temperature can be considered as 0 Kelvin. On that particular temperature, the intrinsic semiconductor acts as a Pakka insulator. So this is a one more question. At 0 Kelvin, intrinsic semiconductor is equivalent to insulator, because insulators are also having the tightly bounded electrons. There is no charge carriers. In the same manner, at the 0 Kelvin, intrinsic semiconductor does not move from one point to another point of charge carrier. So that's why I am going to tell us at the 0 temperature, intrinsic semiconductor is equivalent to insulator. Very important one is number of electrons is equal to number of holes in intrinsic semiconductor. This is the first type. Now I am going to discuss the second one. That one is extrinsic semiconductor. Extrinsic semiconductor. Sir, why you are using silicon? Why don't you use the germanium? Okay, let me discuss. I am going to take as the germanium structure of semiconductor by replacing of silicon, germanium. 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 In intrinsic semiconductor, it is equal to the insulator because of tightly bounded electrons. Now I am going to increase the charge carrier concentration. That means the moving of charges. That means to produce the free electrons. For the purpose of increasing the conductivity, for the purpose of decreasing the resistive value, I am going to add certain impurities atoms. What impurities atoms? If you are supposed to add the impurities atom, this will be, conductivity will be increases. This method, when the intrinsic semiconductor is added to the impure atom, that should be called as doping. That should be called as doping. Doping is the process of adding impure atoms to the intrinsic semiconductor for the purpose of increasing conductivity. Okay? Right. On the basis of doping, the extrinsic semiconductor can be classified into two types. One is P-type semiconductor. Another one is N-type semiconductor. Let me discuss one by one. So, intrinsic semiconductor is a pure form of semiconductor. It has the least conductivity, and then one more important value is the number of electrons is equivalent to number of holes. For the purpose of increasing conductivity, I am going to add an impure atom to the intrinsic semiconductor. That should be called as extrinsic semiconductor. The same structure should be followed, but I am going to change some water. And before that, we have learned the doping process. Sir, how much of impurities you are going to add in the intrinsic semiconductor? Sir, 100 parts per million, 100 ppm amount of impurities should be added to the intrinsic semiconductor. That should be a sufficient one. By the adding of impure atom, the extrinsic semiconductor will be classified into two types. One is P and the N type. Now I am going to teach N type semiconductor. N-type semiconductor. First, N-type semiconductor. N-type semiconductor. Here, I drawn the structure of semiconductor of intrinsic one. I am going to add some impurities to increase the conductivity value for the type of N-type semiconductor. So, here all the atoms are binding in the covalent bond structure. Now, I am going to add the impurities. The process of doping. The 100 ppm value of impure atom should be added to this intrinsic semiconductor. So I am going to add the element of pentavalent. For example, phosphorus and then arsenic. These are all the pentavalent atoms of elements. I am going to add any one of this impure atom to the intrinsic semiconductor of 100 ppm. Okay, sir. Now I am going to add the impure atoms. For example, arsenic. So the center atom is replaced by the arsenic. I am going to add here arsenic. It has the 5 electrons, that is a 5 free electrons. One electron is shared to the top neighbor germanium atoms, and then one more is left, and then one more is down, and then one more is right. So arsenic having the 5 free electrons, 4 electrons is shared to the neighboring atoms, one is remaining. So that electron is here. This electron is called free electrons. So here this is a one segment of germanium binding structure. If you are supposed to connect the number of germanium structure in this binding, you will get a number of free electrons. I already informed you, in a solid structure there are millions of atoms. Millions of atoms will be binded. So you will get number of free electrons. You can able to transfer the charges through the free electron from valency band to conduction band. So I am going to draw the energy level diagram. In a valency band here, this is the valency band structure, energy. The electrons will move from valency band to conduction band. So easily it will be transferred. Here the one electron is extra. This electron only goes to from the valency band to conduction band easily, having certain amount of charge carrier. So the electrons is in the form of beneath of just conduction band, beneath of just below the conduction band. This is called Fermi energy level. Fermi energy level, Fg. This is the extra electrons energy level. So we know very well in a semiconductor there is a little bit forbidden gap energy only allowed. In the forbidden gap energy, the electrons are easily moved from valency to conduction band. So this type of semiconductor is called N-type semiconductor. For the adding of pentavalent atom, you will get 1 free electrons. So number of pentavalent atoms will be added, you will get number of free electrons. These electrons are moving from valency band to conduction band. The free electron energy will be below of the conduction band. That is a Fermi energy level. So here 1 electron is extra to provide the charge carrier and transfer the charge carrier. So the extra charge carrier can be called as donor atom. Donor atom. This donor atom presents in the energy level diagram just below the conduction band. So I am going to represent this is the donor energy level. Donor energy level. In this N-type semiconductor, there is a free electron one is available. So if you are supposed to combine the number of free electrons, the electrons will be getting the majority. So in N-type semiconductor, majority carrier is electron and then minority carrier is holes. Very important one. So that's why we called the donor energy level. N-type semiconductor as a donor energy level. Next, we will see the P-type semiconductor. Again, this is one of the extrinsic semiconductor. In previous time, we learned what is N-type semiconductor. If you are supposed to add a pentavalent atom to the intrinsic semiconductor, it will be converted to N-type semiconductor. In N-type semiconductor, electron is the majority carrier and holes is the minority carrier. There is a donor energy level is present. Now, let me see the P-type semiconductor. I am going to take the same intrinsic semiconductor, that is a pure form of semiconductor. By the process of increasing the conductivity, I am going to add certain impurities. In this time, I am going to add trivalent atoms. Trivalent atoms like boron. By replacing of germanium, I am going to add boron. This is the trivalent atoms. It consists only of 3 electrons. One electron is shared to the neighbor atoms of top, and then one more is left, and then one more is bottom. One more electron is deficiency. So there is no electron to bind the neighbor atoms. So if you are supposed to add the trivalent atom to the intrinsic semiconductor, one electron is deficient to bind the neighbor atoms. This deficient will be managed in a semiconductor. It's formed like in the opposite poles. That means opposite charge of electron is holes. Instantly it will be regenerated. Whenever you are adding the trivalent atom of boron, you will get 1 holes. So there is no electron, there is no free electrons availability in this area, but you will get the holes. By the process of getting the holes, you will accept the electrons to the opposite charge, that is equal to the opposite charge. Every time you are adding the trivalent atoms, you will get the holes. So the holes will be present in the energy level as just above the valency band. This is the valency band. The holes is present in this layer. This is the acceptor atom or acceptor energy level. This is the conduction band. In previous case, N-type semiconductor, acceptor atom is present beneath the conduction band. But in this case, P-type semiconductor, the acceptor atom is present above the valency band. Here, in a P-type semiconductor, holes is the majority carrier. Holes is the majority carrier and electron is the minority carrier. So that's why we call this is the acceptor energy level and then acceptor atom. If you want a more electron, you can use the N-type semiconductor. If you want more holes, you can use as a P-type semiconductor. These are all the 2 types of semiconductor. One is N-type and then another one is P-type semiconductor.